Hi, we're Sedona, Eden, Gloven, Sneha, and Lamia, and this is the analysis and redesign of a gumball machine. The purpose of a gumball machine is to dispense treats and items, and the estimated production volume is over 100,000 units per year. Here's an exploded view of our gumball machine, which we'll talk more about the parts later throughout this presentation. The primary customers remain the same, and our children who want to obtain sweet treats. However, our secondary customers are now adults who may not want a sweet necessarily, but a more art-related thing like tattoo design drawings.
On the screen, you can see our FAST diagram with our primary function being to dispense treats. And in red, you can see that we further clarified what some of our supporting functions are.
Our function component mapping matrix helps understand the functions for all of our components. And you can see most importantly that we have to focus on ice-setting treats and maintaining control.
For our product family design, taking account the different customers, our function differentiation table shows the differentiations of our functions, including contain treats and change location, as well as in our components, changing based on the customers include the globe, spiral cylinder, and the center tube.
For our product family design, our assembly sequence, on the left, we can see the original sequence that includes the variant, and then on the right, we can see the modified sequence to include delayed differentiation. And the slide shows how we used our sub-assemblies to incorporate that delayed differentiation.
These next few slides will show our CAD of our modules as well as the common interface and platform. This one includes our globe, which shows the difference of a cylindrical globe compared to a spherical. The spiral cylinder changing to a box-shaped slit to account for the paper-shaped tattoo designs. For our common interfaces in the spiral cylinder, it includes the cylindrical bands. As well as for the globe, these includes the thread in addition to the globe shape changing from the sphere to a cylinder.
On the screen, you can see our design for manual assembly for our total gumball machine, and the total assembly time was 202 seconds with a 20.7% efficiency. And thus we decided to redesign the module of the globe, combining it with the globe retainer. This would reduce the part counts according to DFA 1, and also reduce fasteners because originally there were screws combining the two parts and they would no longer be needed, as well as add features for easy insertion because of the threading at the bottom. And we also decided to redesign the platform brush assembly. We combined the hopper and globe retainer through alignment and through the alignment nub, which reduces part counts. The alignment nub also added a feature that would facilitate orientation, allowed for easy insertion, and provided locating features. And the tapered interior of the brush assembly also allowed it for easy insertion. So as you can see on our updated analysis chart, the total assembly time did decrease, and we eliminated some of the parts of our total assembly, as well as increased our efficiency by 12.7% without impacting the product function and decreasing manufacturing costs.
For design for automatic assembly, we reduce fasteners by reducing the screws required. We increase part symmetry by changing it from rectangle to square, and we avoid tangling and nesting by adding extrusion, and we cut our assembly costs in about half. On our next is our base cover for subassembly. We add an alignment feature, which also comes with snap fits and a tapered fit for easy insertion, and we cut our costs into about a third. And then from the previous slide, our extrusion will fit into this notch or hole. And lastly, our chute door, we added features to facilitate orientation, avoid tangling, and a Z assembly, just by adding extrusion and adding snap fits to also aid with that Z axis insertion. and we cut our costs by more than half.
For our process selection for our different module and platform redesigns, our first one with the globe, the most critical feature being the long blaze to allow for contained treats prior to reaching the spiral cylinder. This also has a tolerance of about plus minus 0.3 millimeters due to the material and size of the component. In addition, for the brush assembly, the most critical feature being the long slit to allow to guide treats as well as maintain control prior to reaching the hopper, with a tolerance of 0.1 millimeters due to the integral piece of the brush assembly, as well as higher tolerances affecting the functionality. This is just a chart to show how we decided the specific processes of the globe and brush assembly, taking into account the material shape, mass, section thickness, tolerance, surface roughness, and batch. For our globe, we decided injection molding was the best process and machining for the brush assembly.
To account for the design for manufacturing, we put our globe design and our brush assembly design into DfM Pro. For our globe design, DfM Pro suggested that we minimize the draft angle, and for our brush assembly, they had no suggestions that they could give.
Here's the redesign for our brush assembly. Three main features we want to call out is in A, we added radiuses to those sharp corners so that they could be machined. The second changes we made are we changed the hole size dimension from a non-standard dimension to a standard dimension of 1/4 inch. We also made that half circle a full circle that could be drilled through to avoid long radius corners when machined. For our globe design, the three main changes that we made were: one, we reduced the wall thickness from 5 millimeters to 3 millimeters to reduce part cost and solidification time. We also removed the internal threads on the bottom of the globe, so no side pull is needed. And if you look to the right, it shows the new assembly sequence. And then the last change we made was we changed the globe from a sphere shape that has a concave top to a cylinder shape so that there's no internal depression.
Here you can see the cost estimation that we did for the globe before our new redesign. We came up with a part that was $72.10 per part. Then after we did our new redesign, our part cost was $56.74 per part, which is a significant decrease in cost. Then we did the same thing for the brush assembly before the redesign, and we came up with a cost of $9.05 per part. This was then redone after accounting for design for manufacturing, and our new cost was $11.01 per part. And although this is an increase from before the redesign, because of the increase in material, we think that this will still be easier to manufacture overall. Now, here you can see we used hubs to compare the price of the brush assembly before and after our redesign that accounted for design for manufacturing. And we're seeing a discrepancy here between the analytical method and the hubs quote because we were given a lack of data points, which led to an incorrect trend line. And we also had to extrapolate our data. So this could be a potential reason that there is a discrepancy.
For the design of our product service system, this I would create is a feedback format to view customer feedback as well as the complaints. This feedback includes the shape and size, as well as allows customers to send in designs of globe or shoot. In addition to reduce the negative impact of environment, we are reusing the ABS plastic that creates the shoe materials, as well as shipping done, including the materials, is carbon neutral. To conclude, the overall benefits were gained, including the total cost reduction through DFA and DFM. We resulted in a few parts as well as saved 76 seconds. In addition, for our DFM, we were able to decrease the price and save about $15,271 yearly per part. For our pros and cons of design, our pros are the ease of assembly by removing unnecessary fasteners and making it more user-friendly, with our cons being many detailed individual parts, with our material choices having to increase the cost of parts like brush assemblies. Our future improvements to approach include focusing more on a machine that appealed to a specific customer group or industry that allowed for sensible variance, focusing on our FCCM and fast diagrams. And we'd also consider continuing to streamline our assembly to decrease costs and take into account a variety of materials. Thank you so much.